Hey guys, so in this video, I'm going to go over the basics of torque. Torque is just the rotational side of force. So now when things rotate, right, or if there's forces, we want to see if they rotate. So when will you have a torque, as you can see there in the first little aspect, that's when you have a force that causes rotation. So if I have this, if I pull this direction, I have a force, but there's no rotation, so there's no torque. If I pull down, hey, there we go. Now I'm having these. If I push here, nothing. What if I push, whoops, I push down. What if I push up? Right, come on, it starts to rotate. So a torque is when you have a force with a cause of rotation. So now we'll need to look at the details behind that. So what do you have to have for a torque? You have to have a force that is perpendicular to R, and R is defined as the distance from the axis of rotation, so where you're rotating from, to where that force is acting on. So that's the R of one, and then you can see that's the R of the other there. Another way you can look at it is, do you have a distance that is perpendicular to the force? Right? That's alternating version to look at it. If we look down here, there's all kinds of ideas. So this is the first one. If you have a force that is perpendicular. So again, if I looked at this setup, if I pull here, my axis of rotation, let me draw it in. Right. So that line, whoops, can I get it straight now? Right. Okay, that line is my R. So here's my force. I'm pulling this direction, but my hand is pulling parallel. So my force is this way. So that's why there's no torque. If I push, the same. But what about when I push up? Right? When I push up, it starts to rotate because the force is up, and that is perpendicular, right, to that R line I had drawn on my paper. You can also see if the force has a perpendicular distance, which we'll look at, and that perpendicular distance is also called a lever arm, which we're going to see right here. So let's look at the lever arm idea. So here, I go for my axis of rotation, or how to get a lever arm. This is really important here. So extend your force line. So I just take that line and draw it forever. And then I go to my axis of rotation, and I intersect that at 90 degrees. So those two, the force line and my distance from the axis of rotation to that force line should be perpendicular, and that's my lever arm. So all of these have the same force, and so you can see how long that lever arm is. It's the length of the wrench. This next one, again, extend this out. I go for my axis of rotation, and again, intersect that at 90 degrees, and that's my lever arm. Now remember, before, the wrench length was my lever arm. Now, here's my wrench length in red, and R is my lever arm right there. Or excuse me, this blue line is my lever arm, and that is a component. And we've seen this over and over and over again, that components are always less than hypotenuses. Here it's even more exaggerated. Force line, extend that out, axis of rotation to that force line, there's your lever arm. So that's lever arm. Now let's look at some scenarios where there'll be different ways to look at it. So let's look here. Again, torque can be force that is perpendicular to R, or torque that is a force times a perpendicular distance, which we're calling lever arm. So the axis of rotation is up and down infinitely. Okay, so on this one, right, so do I have a force that is perpendicular to that axis of rotation? Yes, this is pushing in. That'd be like, here's my axis, and I'm pushing this way on the door. If I pushed at that angle on the door. Right? So I have a force that is perpendicular. This I have, right? But what about my R? That's the distance from that axis of rotation to that force. So if you push on the axis of rotation, as you know, that is not going to rotate. It has no torque. Okay? What else? What about lever arm? So if I wanted to try lever arm with this, extend my force line out. My axis of rotation is up and down. And remember, lever arm is the perpendicular distance from axis of rotation, to force line. So if those two things intersect, your lever arm equals 0. There's no distance between them if they're touching, right? It's like, here's my force line, here's my axis of rotation. Hey, there's a distance. But if they intersect, what's the distance between them? That is 0. So that's why you don't have any torque. It won't rotate if you push at F1. F2, right? Axis of rotation to my force, the origin of my force. So now I have a perpendicular distance, so that would cause it to rotate. What about lever arm? Extend my force line out, axis of rotation, intersect that, perpendicular. They're the exact same. So either one of those would work just fine. Now, one thing I did want to talk about that I jumped over is, remember when we did forces and we said if I push on a box, and we just drew the free body diagram there? Well, now that doesn't work, because if you push on a box here, here, or here, if this is your axis of rotation, let's just do the top two, they'll do different things. If I push in the axis of rotation, that's just like F1, it won't rotate. But if I pushed here, right, and I extended my force line out, axis of rotation up, I'd have a lever arm, that one would rotate. So for rotation, it's really important that you pay attention to where that force is acting. F3, right, extend that through, it goes through my axis of rotation, so lever arm is 0. Or I could say none of that force is perpendicular, all of it is parallel, would be how you'd analyze that one. One thing you'll start to notice is if you pulled both of these ways, if this was my axis of rotation, again, I have a lever arm, it's going to rotate, and we'll start getting into clockwise versus counterclockwise. So that one would have a torque, so it would rotate clockwise. Here's a wonderful example with a broomstick. Hey, if you think about this one, they're saying it's very difficult to have a broomstick this way, and it's easier when you tilt it up. And I'll show you one here in just a second how that works. So let's look at it two ways. Torque equals F perpendicular to R, and torque equals F times that perpendicular distance, which we're saying is the same as lever arm. So here is my R, and here is my force. All of the force is perpendicular. If I did it here, from the axis of rotation to the force, there's my R. The R is the same in both values, but on this one, only some of this force is perpendicular. If I drew components in, let's call this X and Y, only the Y portion, does a torque. So it has less perpendicular force to create a torque. Lever arm is the way I like to look at it. So if I look at it here, the lever arm is the length of that rod or that stick. If I do it here, there's a cool visualization for it. Okay? Extend that force line out, go to the axis of rotation, and here is your lever arm. So it is not the entire length. Remember, this is now a component of the entire broomstick. So this has a smaller lever arm. So now let me try and show you guys this and let you see what that looks like. Right? So here is my broomstick. Right? So if I hold it here, my hand gets really tired. I even have to try to put my thumb out a lot of the times to balance this. Right? So if I do that, it hurts my hand. I can really feel it here. But as I go up, it's getting easier. And let me show you why. So here, the force is acting downward, axis of rotation, all the way to that force line, acting perpendicular, so it's the entire length is my lever arm. As I go up, now it's getting much better. I can pull my thumb down. So again, that force acts straight down, because it's gravity, so gravity acts straight down, and look, how far is it from my hand? Not very far. As I get upward and upward and upward, Now that force is going down here, and it's only about that far. If I go completely straight, it's so much easier, and that's why it's so much easier to hold something like this. This is why you can balance heavy things, okay? They don't want to rotate much if you hold them like that. Now my hands are really sweaty, okay? But as you can see, I should be able to balance it, or at least it's not going to hurt my hand to try and rotate. As I go there, okay, don't lose it. It's a lot harder when you do that. Take some time and try it. Again, that's why I love physics so much, is because we can just test it out with kind of anything we have at our house. Okay? I don't know if your parents will let you do it with the groceries, but maybe take something else and try it with that. Here's a couple of examples of finding out lever arms, or let's just try and find torques. So torque equals F perpendicular to R, and in the formula chart, it is FR sine theta. Now, it's not any angle. It tells you it's the angle between these two things, right? Or torque equals F times L. So let's see which one's easier if we really need to know both of those. So let's think about, would A rotate? Back to my paper. Right? The axis of rotation is right here in the middle. And that force, whoa, it's already rotating there. Okay? That force is acting somewhere over here and going down. It rotates. Okay. Let's see if we can now prove it with the physics. So, axis of rotation to the origin of the force. That is my R. Is some of that force perpendicular? Yes, 100%. If I had to zoom in, okay, I could break it down into these two components. So let's call that X and Y. So that Y component does matter. If I had to find the trig, I would have to find that angle. Right? So if I had to do this, the force is 2 newtons, based off of this being 2 boxes. And we'll say that lengths are measured in centimeters, so that's more reasonable. So to find this long length, I'd have to do trig. So 1, 2, 3, 4, 5 centimeters, and I believe counting this one up here is 8 centimeters. So we could do a squared, b squared, a squared plus b squared equals c squared to solve r. But then I would also have to get the perpendicular piece. So sadly, I can't even do this, but I could do that here. I could do 2 times a squared, c squared, whatever, bigger than 8, less than 13, and then I'd have to find that angle. So I'd have to do trig. I know all the sides. I need that angle. So that's kind of ugly. Let's see if lever arm is easier to find. Right. So how do you find a lever arm? Extend out your force line. Go from your axis of rotation and intersect that force line at 90 degrees. There's your lever arm. So this is 2 newtons, and this is 1, 2, 3, 4, 5 centimeters, so 0.05 meters. Seemed pretty easy to me. So don't be afraid to use that method. Right? Let's look at C, since I'm right here. Axis of rotation. Okay? If you pull right on the axis of rotation, what do you think is going to happen? Nothing. No rotation. Let's prove why. Well, axis of rotation, force line. If they're touching, what's the distance between them? Nada. Nothing, so that one won't rotate. Lever arm equals 0 on C. B, again, if you had to do axis of rotation, distance R, it'd be ugly. Looks like it's going to rotate because there is some perpendicular component there. Again, the trig gets ugly, so I like to do lever arm. Okay? Just extend out your force line, go to your axis of rotation, and intersect at 90 degrees. 1, 2, 3, 4, 5, 6, 7, 8. 8 centimeters, and you're good to go. E. Okay, what do you think about that one? All right, hopefully you got an idea. E is the force line goes through the axis of rotation, back up to what we saw before. Lever arm is 0, so won't do anything. D gets real ugly. You'd have to do trig either way because my force line is extended already. Axis of rotation, intersect that It's bad. I don't know. It's hard to get 90 degrees on that one for me. So maybe if you had a protractor again, that was something you could have used before, but figure that out. I think that all the other ones are going to be more similar, so that's what you need to be prepared to look at. Roll through a couple more. Rank the magnitudes of the torques applied about the center for each one of these. So, force through the axis of rotation, torque equals 0, lever arm equals 0. Lever arm equals 0, torque equals 0. Let's look at these two. So, axis of rotation, intersect that. There's my lever arm. It says each of these sides of the triangle is 1. Okay? So this one, extend the force line out. There's my lever arm. Those look the same, but I'm not quite sure. That's starting to get into a little bit of trig. We'll come back to that. So maybe it's easier to do the other way. Maybe it's easier to do the torque equals F perpendicular to R. So let's look at R. So R, axis of rotation to the force. There's R. Now this one, R is from axis of rotation to the force. There's R. I can see all of that force is perpendicular, and on this one, I see only some of that force is perpendicular. So AC, B equals D. A is greater because A has all the force perpendicular to R. That'd be the big piece there. The other ones, D and B, are 0 that we would have there. Let's show you lastly the other one of if you wanted to solve it with the trig and you were comfortable with that. So remember, that's the lever arm there, and that's the lever arm there. So it says these triangles, each side is 1 meter. So we can see for A, it's 1 meter as the lever arm. C, this is the lever arm. Well, again, this is the hypotenuse. The red is a component, so it has less. So you could say B has a smaller lever arm because the lever arm equals a component, not hypotenuse. Something along those lines. Right? Nature of time, let's skip that one. Right? So let's look here. If an angler were to cut a rod, how would the weight of the piece on the right side compare to the one on the left? So here it says it's balanced. So that means the torques have to be balanced. So here's my axis of rotation. So this is where center of mass comes into play. All of this mass on the right side, okay, so we'll say all of this mass has to act at the center, so it's going to go right there. And all of this mass acts at its center right there. And the blue one causes a torque this way. That would be clockwise, yep. And the black one creates a torque the opposite way. So those torques have to cancel each other out if it doesn't move. So remember, torque of black, we could say, equals torque black and blue. So here they have to equal. So that would be their force of gravity times their lever arm. And so I can see here's the lever arm on this one, and here is the lever arm on that one. So here, if this side has a bigger lever arm than the other side, it must have a smaller force. And so that's how you could look at that one. Since it has a bigger lever arm, it must have a smaller force to analyze it that way. We'll skip down to this one. If you wanted to look at some of these, okay, is the torque about F1 clockwise or counterclockwise? So this is when you start to get into multiple pieces. So again, it's about A. So let's think about which ones even produce a torque at A. So here, this one goes through A, so 0 torque. The next one, F3, I could do it like this and say that's the lever arm is right there. And then I have to find the lever arm of F1, so extend that force line out, axis of rotation there. What's bigger, a side of a square or through the center? And I would say through the center is more. So F3 is going to have a greater amount of torque. Or sorry, F1, it looks like, has more torque. So about this location, if I held it there and I pulled this direction, that would cause it to rotate this way. If I held at this pin and pulled this way, it would cause it to rotate the other way. But we said the one with greater torque is F1, so that is going to go clockwise. About B, right? Let's try one more together. This is adding in multiple pieces now. About B, so this one, if I extended that force line, there's the lever arm of B. Aside, intersect that perpendicular, there's the lever arm of 2, smaller, and 3 goes right through. So I know that, again, F1 has to do more about B. So it is going to be, again, clockwise again. So those are some you can practice on those, and I'll put my key down for these. But hopefully that's an intro to you guys for torques and the rough idea of how to calculate those.